right, so yesterday and last night I mentioned that we are under the EarthLight umbrella creating and be rolling out the New Worlds Institute. I mentioned some of the more, shall we say, in the aerospace establishment's face projects like Don't Deorbit the Station, these kinds of things. But one of the great projects we're going to be developing, we're going to talk about right now, and that is the idea of, given the fact that, as you may have heard last week, we just failed to hit the 1.5, the climate change initiatives that would lead to stopping the heating by 1.5 degrees centigrade. That's not a good sign, and pretty well predictable given the governments that are basically in charge of the entire planet right now. So the idea here is, what if we were able to put something together that would slightly reduce the amount of sunlight that hits the Earth? And that is going to be one of our projects. We put these under the umbrella of what we call EarthSaver. EarthSaver includes power from space, planetary defense, two different things, and then EarthShade. And to talk about that, which is going to be one of the very first projects we roll out, we have Luke Moloney, who is a serial entrepreneur, and Hart Traveler, who is from Rensselaer Institute. I'll let them explain the rest of this to you. We'd love to get you engaged with us as we move forward. The websites that'll be talking about this will start rolling out in the next 30 days or so, and you'll be able to really dive in depth. But they have a great presentation. Thank you. Luke?
Thanks, Rick. Hi, everybody. Oh, there's the slides. Okay. Talking about this project I've been working on for a long time, and I want to thank Rick for inviting me to come here, and I want to thank the organizers for putting me after Metzger and Zubrin. Easy acts to follow, yeah? So Project EarthShade, this is a project I've been working on for a long time. It's sort of a subject I've been researching on the side, and a few years ago I wrote a paper with my colleague Hart here, and I never really finished it. I was going to present it at this event in 2019, but then I didn't, and then the pandemic happened. And so since then, it's kind of sitting around, and I decided to turn it into a little presentation rather than a paper. So climate change mechanisms, we know about a lot of them. For example, the sun output is changing. The sun is warming up over time. This is going to cause a really serious climate change problem in the long term. In the 100 million years or so, Earth will probably not be habitable anymore. As Metzger mentioned, celestial body impacts affect the climate. It must have been a terrible weather the day that this Theia object crashed into the proto-Earth. There's also various different chemistry changes happening in the atmosphere, not just the CO2 that's happening right now, but here we got a graph of the oxygen catastrophe, the great oxidation event that happened a long time ago when life evolved the ability to create oxygen. And the climate changed dramatically, but you can see from this graph, the time scale at the bottom, it was much slower than what's happening right now with CO2. Volcanism is a natural process that affects the climate. Volcanoes have a big impact on the climate. Here we see the effect of the optical density in infrared of the Earth after the 1991 Mount Pinatubo eruption. Volcanoes have been erupting since the beginning of Earth. They will continue to erupt for a long time, and we have to deal with the prospect that there may be much bigger volcanoes than Mount Pinatubo, and we may even have igneous provinces in our future. Life affects the climate. We are part of this effect on climate change, even without the technology that's accelerating it. Pictured at the top is the snowball Earth from the, I think called the Huronian era, where the Earth was presumably frozen almost completely over. There was very little life at the time, and the sun was cooler, but the temperature of the Earth right now is about 13.9 degrees Celsius global average temperature. That's up about a degree from the pre-industrial era, and it's probably going to continue to warm up. But without life on the Earth, it will be much, much colder. It will probably be nearly a snowball Earth. And finally, we get to anthropogenic changes. There's many processes we're doing. Of course, there's CO2 emissions, but in this picture, I show a feedlot. Cattle give off a lot of methane, but also this sort of industry represents a very large external carbon cost to create the food for these animals and deliver them to a central site. Now, how can we mitigate climate change? There's many things we can do. Pictured here is the IPCC Report 5, some scenarios of reducing carbon emissions into the future. But it's important to note that even if we reduce carbon emissions to zero very, very soon, much of the carbon-based climate change is baked into the atmosphere already. It's already in the atmosphere, and it will continue to cause global warming. It will come out of the atmosphere slowly through weathering processes and so on, but it will take a long time. Ocean fertilization is another strategy you may have heard of. The idea is you fertilize the deep ocean with certain nutrients that encourage the rapid growth of plankton, and the plankton absorbs CO2 from the atmosphere through photosynthesis, and then as it dies, it sinks into the ocean, sequestering the carbon deeply. However, as they die and sink, they degrade, and they give back a lot of the carbon to the atmosphere and to the shallow ocean. So recent studies indicate this is actually not a very good solution for dealing with decarbonization of the atmosphere. This is another approach. There's various different strategies. Here's a balloon strategy to inject aerosols into the stratosphere. The idea being that if you disperse very fine particulate of sulfur dioxide into the upper atmosphere, it will persist in the stratosphere for a long time. And this makes the atmosphere rather opaque to, rather reflective to infrared. So a lot of the infrared radiation that might otherwise get into the atmosphere gets reflected back into space. This mimics volcanism, so it's a natural process. There are some downsides. For example, the sulfur dioxide comes out as acid rain eventually, and it can cause ozone depletion, and you have to keep doing it indefinitely, because if you stop doing it very rapidly, the effect goes away, and we're back to the climate change scenario, the global warming scenario. Ice cap augmentation, there's various speculative strategies for increasing the density of ice caps. As we probably have all heard, ice caps are losing a lot of mass, particularly Greenland, and, but we could install enormous fleets of solar or wind-powered artificial snow machines and make more snow to make those ice caps thicker. It's a big project, you know, it costs a lot, and you know, has the potential risk, if you go too far, you might end up in an ice age again. Another strategy that I've heard of, I haven't really studied it, is subglacial dewatering. So glaciers have water melt underneath them. That lubricates the glacier so it slides faster. Plus with warmer summers, as the globe warms, the glaciers get softer. So they're moving faster. They're slumping faster into the ocean. The idea with glacier dewatering is you drill down, you pull out that water, and then you slow down the rate at which the glacier moves. And finally, we get to space-based sunshades, the purpose of this talk. And this is the solution that I am in favor of. However, what solution should we do for these climate change? I think we should do all of them at the same time, right away. So the basics of the sunshade, this is pictured from Roger Angel's paper from 2006. It's a really great paper. Look it up, Angel 2006. He goes into a lot of the aspects of sunshade dynamics. And here you see the geometry of the solar system. You have the Earth, you have the sun, and in between is the L1 point. That's approximately where you put the sunshades, approximately. And now here we have the schematic of the sun's Earth-Sun system. L1 is the Earth-1 Lagrange point where the gravitational potential is balanced. If you put something there, and in theory, stays well. However, it's a metastable point, so you actually still need a bit of interaction. Now, the sunlight will actually push the sunshade a little bit, and we're talking about very, very tenuous structures, so they'll get pushed easily. So we have to put them closer to the sun, where the sum of the solar radiation pressure and the Earth's gravity equals the sun's gravity, as here. I call this radiative L1 or RL1, and that is, to give you numbers, like the L1 is about 1.5 million kilometers towards the sun, and the RL1, depending on the density of the structure, is 1.8 approximately million kilometers sunward. Here's an example of the, again, a graphic from Angel's paper. It's an example of how it might be built. He imagines these discs. The size depends on how we build them and how big we build them. But the idea being is that they're made of very, very, very thin glass. You see about just over a micrometer thick. And it's a micro-diffractive glass, which means that at very, very low mass, you can diffract some of the light. Now, I'm saying diffraction rather than reflection because if you reflect the light the sun imparts more momentum onto the structure, so it has to be closer to the sun. So you can get an overall lower mass to the sunshade system by using diffraction and just bend the light a little bit so it misses Earth. How big is it? It's pretty big. So if we want to shade about 0.5 to 2% of the sunlight from reaching the Earth, there are various different papers studying how much we need to reduce the sunlight by. Some people say 0.5, some people say 2. In this study, we're saying about 1.8. That means we need to make a structure that's about 6 million square kilometers of this diffractive material or reflective material. We have to block about 6 million kilometers of the sun from hitting Earth. That will lead, oh, by the way, 6 million kilometers, that's, if you imagine it, that's a circle about 1,400 kilometers in diameter, a little bit less than 1,000 miles for you Americans, and it's about 70% the size of Puerto Rico. It's a big thing. It will weigh about 20 to 25 megatons if it's made by this very, very, very thin glass. That is, for reference, about the mass of this dam pictured here, the Grand Coulee Dam in northern Washington. It's a big structure, but that was built, mostly by human labor in the Great Depression. Where do we build these things? Where do we get them? So here's a quick analysis of what it takes to launch them from Earth. If we build them on Earth, we have the industrial capacity, but can we get them there? So quick calculation yields that if we launch it on a Falcon 9, it's about 1 million Falcon 9 launches. If we launch it on Falcon Heavy, it's less. If we launch it on Starship, it's going to be about 300,000 Starship launches. Quick math says that if you launch 10 Starships a week for about 600 years, you do this. Now, obviously, that's a bit impractical, and the amount of the impact from that is insane. The CO2 created just from these launches is enormous. If we use hydrogen and oxygen rockets, obviously they're not producing CO2, but where do we get the energy to build to electrolyze that much hydrogen on Earth? We don't have a solution for that. The amount of heat created will heat the atmosphere enough that there will be like outsized effects of global warming just from the impact of the rocket launches, just the heat, without counting the CO2. Also, they're expensive. About $35 trillion to do this number of launches, projecting a reduction of cost in the future without projecting new technology. That's just for the launch, not the production of them. There are better ways to launch from Earth. A couple of years ago, I was here, begging on this same pulpit in favor of mass drivers. If we could build mass drivers, we could launch a lot cheaper with a lot less environmental impact. But we don't have mass drivers yet. And if we're going to build a mass driver, why don't we build it on the moon? So a quick study of launching from the moon. Here's a cartoon graphic we got from a space fan art site that indicates a moon launch facility with a mass driver. So if you launch from the moon, there's way lower delta V, about 2.9 meters per second from the moon to Earth-Sun L1 compared to greater than 10 from Earth. Also, the moon has no atmosphere, so you can just do a single-stage launch from the moon. To build this facility here, it's got a solar power, atomic power, landing pad, launch facility, a lot of stuff. It's going to be about 17 Falcon Heavy launches, 30 to 25 rovers, big project. So we build this, we start launching. Then we build more of them, and we build more of them. We build about 40 of these facilities on the moon, and we run them for about 40 years, and then we can build this structure. It's going to be expensive. You can see there I put down, there's a line at the bottom. It looks like it's a straight line. That's the cost of the infrastructure, about $100 billion, which will be a number that matches a number Hart's going to show you later. And the cost of production, who knows, we might have self-replicating machines that'll bring the production cost down, but we're looking at about $6 trillion within an order of magnitude. Future is going to bring the costs down. We could get it from asteroids. We're a little bit, this is a bit outside the scope of my expertise and anybody's expertise at this time, but theoretically we could capture an asteroid, bring it to the Earth-Sun L1 point, and it would directly shade the Earth, in addition to being a feedstock for for additional production. I am in favor of a heterogeneous approach. I don't have the right solution. I want creative minds to come up with better solutions. Now, if we can build this structure on the moon to launch this structure into space, we're digging up massive megatonnage of regolith and refining it. What else can we do? The sky is not even the limit here. We could build a solar flare shade. This sunshade will actually block a little bit of the solar flare, but we could build other structures to prevent future Carrington events. Space-based solar power, you might have heard of it. It's one of the ways we could reliably decarbonize all of Earth's energy grid. We don't need fossil fuels on the energy grid. We don't even need atomic power if we have space-based solar power. There's so much energy into space, but the structures to collect it would be big. So why not build them in space from resources from space? If we are mining all this refined glass on the moon, we're going to have lots of other products, like aluminum. Why not take that aluminum, turn it into extrusions, use the same mass driver to deliver it to customers in space who are building whatever kind of megastructure? For example, maybe launch assist structures. We could be building rotavators, orbital rings, all sorts of futuristic launch structures around the Earth. We could build a hypothetical space elevator if we had magical materials too. Orbital shipyards, you know, if we have all this material in space, this construction capacity, future spaceships will be built in space from materials collected in space. And these shipyards will be built in space from materials collected in space. And of course, space HABs. We all want to live in space. We want to see a future where humans can live in space. We're going to build big, huge structures in space where people will live. Some of them will be orbiting Earth, some will be orbital cyclers, and some will be orbiting the sun. Heliocentric space habitats means we're taking our first steps towards becoming a K2 civilization. Now, what if we don't do this? For this scenario, I'm going to turn it over to Hart, who's done this analysis on the cost of inaction.
Cool. Thanks, Luke. All right. So, hi, everyone. My name's Hart. I will cover the cost of inaction section. I'll be moving fairly quickly, but I'll summarize with key points where needed. In the interest of time, I'll leave out some details, but if anyone has... Sorry?
Lots of time.
Oh, yeah? Oh, okay, cool. All right, so maybe I won't leave out all the details. Where was I? But yeah, if anyone has any questions, we can review material in the Q&A after the presentation. Quick note, we're also in the process of constructing an interactive website to visualize both the data I'll be presenting here, along with a number of other cool insights related to stuff like insurance data patterns, sentiment, and awareness gathered from the GDELT project, along with some other assorted cool stuff. And that's still in progress, but if you want to see like the sort of broken version that we're working on, you can find it at miamilost.github.io. Yeah, so we'll be contextualizing the sunshade cost through an estimate of the economic impact of sea level rise on Miami. So we'll start by looking at a historical view of global sea level rise, or SLR for short, as I'll call it, over the last 30 years. On the left, at least, you can see the last 30 years are shown, and data from the last 3,000 years are shown on the right. The 30-year timeline looks sort of like it could be captured in some sort of linear model, but when you expand out the temporal horizon to the last 3 millennia, you can see that the trend is substantially more complex. This doesn't actually apply perfectly to Miami. So one important thing to mention is that SLR in Miami is substantially higher than the global mean rate of sea level rise. In their 2016 paper, Dowinski and several other co-authors found that sea level rise along the southeastern coast of Florida could be up to 3 times higher than the global mean. So to evaluate how sea level rise might affect Miami, we use the bounded region shown on the left. You can see that we've included an elevation distribution produced with topographical data on the right. There's a clear jump in the amount of area covered under 1 meter of elevation above the sea level. This leads to what we call the sea level rise inflection point, or the big SIP for short. The SIP represents the period of time when, as the sea level rises, coastal inundation will go very quickly from being manageable to potentially catastrophic. And this sits sort of in the range of around 1 to 3 meters of elevation. You can see that around 3 meters it reduces to pre-SIP levels. So what would this SIP look like? Well, we reconstructed what it might look like using image and elevation data from publicly accessible satellites. The image on the left is more or less what Miami looks like today, and the image on the right is what Miami might look like as the SIP finishes off, a sea level rise approaching roughly around 3 meters. Given the significance of the SIP, it seemed worthwhile to estimate when it might begin. To do this, we pulled down data from the IPCC, specifically their sea level projections from the AR6, the Assessment Report 6, This data allowed us to generate probability density functions of sea level rise at 10-year intervals. These PDFs can, in turn, be used to estimate the probability that SLR will fall within a certain range in a certain year. To compute these values, we integrate the area under the curve between the SIP starting point out to infinity, though the probability decreases exponentially. So, it's a finite amount, of course. If we do this for each probability density function with an assumption that the SIP begins maybe around 900 millimeters of sea level rise, we get the following probabilities going out to the year 2100. That's on the right, or 2150, I think it actually is. So there's a 60% likelihood that the SIP will have started by 2150, at least according to this method. But there are a few things to keep in mind. So the first is that, as mentioned earlier, the local rate of SLR may be up to 3 times higher than the global rate in Miami. And the second is that we don't actually need to wait for the SIP to occur or major sea level rise before large parts of Miami become unlivable. So take the most recent disaster. Here's a still from a video taken in Florida before the storm surge in Hurricane Ian. And here is a few minutes later, after the storm surge had arrived. So even if one says that there's a 60% probability of a SIP arrival 130 years from now, which, remember, due to local SLR, 2 minutes? Oh, okay. All right, I'll speed up a little. Underestimates the probability. Even if we assume that's true, we probably don't need to wait until the SIP arrives for economic and humanitarian costs to begin to materialize in an existential sort of manner. Won't be the end of America or civilization, but could still be pretty bad. So we looked into what the pre-SIP costs might be, and thankfully the U.S. Army Corps of Engineers did an analysis on this exact topic. I'm going to speed through this part a little bit because we're short on time, but it would probably cost about $3.1 billion to establish flood-proofing, raise elevation. It's worth noting that if the sea level continues to rise, these proposed solutions are a quick fix, not really solving the root cause of the problem. The total pre-economic cost of extreme weather events, specifically hurricanes, in Florida over the last 7 years comes out to around $364 billion. And these also claim the lives of just over 4,500 people. So if we use the FEMA estimate for the statistical value of a human life, which is $7.5 million, that adds another $34 billion. I'm going to speed through this last bit a little bit. Just give you guys the main statistics. Total infrastructure in Miami, critical infrastructure, is around $103 billion. You can contrast this with similar events like the 2018 California wildfires, cost around $148. If we move on to the next slide to the conclusions. So I had a lot here. I'm just going to kind of skip through it and give you guys the core figures. When you account for a bunch of different factors, you get a value of roughly maybe around $1 trillion. And it's important to keep in mind that this 1 trillion figure is just really the area of Miami. So there are dozens of other cities which we're going to need to protect and adjust for. And overall, it gets into the trillions. And of course, potentially, we're facing like thousands of people dying prematurely. So yeah, it's a pretty big deal. But if we find ways to address the root cause of the problem, then I think we can avert it. That covers my section. Luke, do you want to?
Yeah. So, I kind of messed up here. So what can we do? This is an enormous project. This is a cathedral scale project. We will die before this project is complete, but we should start it. So what can we do? Well, first of all, the New Worlds Institute is going to start to agitate for this. We're going to start to agitate to national governments, to space agencies, that we've got to do something about this. For example, we could do a Pathfinder mission. We could build some of these spoilers, fly them in space, and collect interesting science along the way. We can start raising awareness. Perhaps we can get it into television shows and movies. We could agitate to NASA, for example, Space Force. This is a planetary defense initiative. And we really have to have a lot more people thinking about how to solve this problem. We need creativity. So please join us. We're out of time. We're running late. There's going to be no Q&A, but networking break is coming up. You can ask me questions there. Ask Hart questions. Look at his website. That's all we got.
Thanks.
I want to thank Damien Kloger, who's in the audience here, for all his help getting this presentation together. Thank you very much, Damien.